Okay, thanks for reminding me. So now that we have a list of facts, what we need to do is to transform each fact, okay, into a sentence vector. So what is the map? I have this fact. I need to map it into a vector for each of them. So if I map each of them and put them as a row vector, the overall matrix will be the matrix where each row represents a fact, okay? And we can do this using our embedding functions. So go ahead and fill in the send vector, okay? So this should be a matrix where each row represents the embedding of each fact, okay? So go ahead and write this and send me the code that you have. I would like to make sure that you are following and implementing with me. Do you have the lab open? So go ahead and implement the fact. Regarding the first part of the code, just use the simplest embedding, or just one line of code. Okay. Now we want to call that embedding for each fact that we have. Okay, embed them into a vector and have them. You can make them a list of vector and do it a NumPy array based on that. Okay, so it turns a word into a vector. Yes. A word when we're talking about word embedding, a sentence when we're talking about sentence embedding. Okay. But the basic building block is word embedding. So I can show you here. So here you have an example. So in an embedding, what you have is that if you have, for example, men and women, a good embedding will do what? It will tend to embed men and women close to each other. Okay, men and dog far to each other, and dog and cat, for example, close to each other. So the embedding also encodes the semantics that is behind. Okay, such that if you compute the similarity between men and women, it will be smaller. So if you have men and women, it will be smaller than the similarity between men and cat. Okay. So
how this and that?
How they work?
No, how this vector? How is it appeared in the vector?
How is it?
What is in the vector?
They are values, just numbers.
What are those numbers? What is the
those numbers represent the length of the vector is defined by the embedding that you use. Okay, and regardless of the size of the input, it should provide the same size. Okay, so when you're embedding by specifying the files as well. Okay, so regarding how the embedding works, that was the topic of today's lecture. Okay. Yes. Yesterday lecture, yes. Yesterday lecture, yeah. So here we are just using the existing embedding function that are having the guarantee of providing those functionalities. So does any one of you have the code to share? Okay, still working on it. Once you have it, just send it in the chat. So this can be done with one line of code, of course. So here, what we can do, for instance, is to call our embedding. In fact, okay, with the facts coming off from the list, our list of facts. Okay, and then this one, we will expect it to be in NumPy. So we'll put it in the NumPy array. Okay. Well, so after this, we can check the size, can check the shape. So if you check the shape, you see that it has 159 rows and 384 columns. Okay, so each rows represent one fact that has been embedded into a vector of 384.
Yeah,
Show embed again, yes. Let me just send it in chat so you can have a look. So I sent in the chat. Well, so now that we have our matrix of where each row is representing the embedding, we can now do what? Given a query, we may want to find the 5 facts that are closest to that query, okay? Using the cosine similarity. Okay? In this case, you also need to embed your query. Once you have the vector representation of your query, you have the vectors representation of your documents. We can then compute the cosine similarity between them, sort them in descending order of similarity, and return the top k. That means the top 5 in our case. Is it clear what you are expected to do here? So initially, I have my set of so where each we have one, it is document 1. We have document 2, document 3, and so on. So these are documents or just sentences. Okay. So what we do next is that we perform the embeddings. Now in the embeddings, what we have just set of vectors. So here it's vector for the first document, vector of the second document, vector of the third document, until the vector of the last document. At the same time, now we have our query, which is just like a text. We use the same embedding. This is exactly the same. So we use the embedding. And we get what? We get the vector. Let's call this WQ. So this is, let's call this WQ. Or let's call this W prime. So this is just the vector of our query. Okay. Now what we want to do, we want to retrace the vectors that are most similar to our query. Okay, so we compute the similarity. Between what? Between each Wi and W prime. Okay, so when you compute the similarity, we have a value. So if you do it for each of them, you have a vector of similarity. So where you use the similarity between Wi and W prime, W1 and W prime, W2 and W prime, until the similarity of the last document. And then we do what? We sort them. And return the top key values. Does that make sense? So this is the process. Similarity-based retrieval. Once we have the embeddings, we can then use the embedding to compute the similarity. Remember, the embedding also accounts for the semantics. So your search engine is expected to perform way more better, or at least more better than the search with just the term frequency count. So go ahead, share, embed the document, the query, and then compute the cosine similarity between that query and each of the vectors of the documents. Sort them and return the top K1. So you will have around 15 minutes to do this. And I want you to do it yourself and then share your code. You can use built-in functions to compute the cosine similarity. That's pretty fine. Or you can implement it yourself. We'll grab a cup of water and I'll be back. Well, so as I said, it's really that nobody shared the code. Do you have a code to share? Well, so here, what you need to do is first you have to also embed the query using the same embedding that you had before. And after embedding, we can then use the cosine similarity as we did here. Okay, so you can use the same cosine function. So we can call cosine between the query and sentence vector. So here you have the similarities. Okay. So. So let's print this and see, or let's check the shape. Okay, vector should be one dimensionality. We cannot specify the well, so let's look through each vector. So here we have enumerate. And then if we create a list of similarities. Can do what? So for each vector, we can append, for instance, I. And the cosine between the embedding of the query and the document. Okay. And after that, we can wrap this in a function, find k closes. Where we have the query, the documents, and the value key. So here should be the document. And what we return the sorting where we sort them. So we return sorted. So we sort the similarities based on the value of the similarity. So here we use lambda expression. So for each pair, we return each pair the first value. That will be the cosine similarity. And we can have it in reverse order. So we have reverse true. And okay. And then return the top key. Why? So it's an issue here. Similarity is not defined. So from the find top k, we return the find top k with the query, the vect, centers, and then the top 5. So slides not tuple. So here we have to break it with the similarity. So we can also print it with similarity values, okay, which will be exactly the similarity that we got from the list. So it tells us that for the query good mode, this is having the highest similarity. Which okay. So in the next task, what you have to do, you have to repeat the same thing using each query, and then you have to compare them. So I will leave this for you to do it, because it seems like you are not working in this lab. I'm not sure you're even listening to me. I hope so. But what we're gonna do next is to, okay. Oh, okay, it's fine. So here, but something that is interesting is that this cosine does not seem that accurate, because when we type good mode, it does not return anything related to good mode. Okay, so let's compute it by ourselves. So here For the query, let's compute the norm. So query norm will be equal to query divided by, okay, let's take it like this, will be equal to query divided by the norm. So we can use np dot lean algebra dot norm. And then we can do the same with each vector. Okay, so for each vector, we can compute what? We can compute the norm of the document, which is equal to V divided by the norm of V. Okay, and then for the similarity, we just append np dot mat mul of the query norm and the norm of the document. Which should be it. Let's check what isn't working. Cannot convert string into, oh, now I got. Resume. Anyway.
We will start the combination.
I think they didn't lose much about.
Resistance. Can you start?
Okay, let's try.
Let's redo that.
I think we don't have the time. So basically, in the whole data set, you have the information about the polygon, the shape, and all the things that you can, the point that you can connect, okay, by draw lines. That the final image will have the head itself, okay? And then you have also points. We have more than 2 million points that are located. So you have a file that is indexed and tells you that in this particular coordinate, I have this point and this information. So we can map them like this. So you can see these scaters that represent all the points that we placed in the map, okay? So your task is to build an index for that, how to index those points and query the index, okay? For instance, if you are given the coordinate of a city, we want you to retrieve, for example, points that are located inside the city, okay? Or if you are given, for example, the name of a point, you have to query your indexing, okay, to find the points that are having the same name. If you are looking for a coffee, for example, okay, have to use the embedding that we did before. Search by embedding, not search by terms. Okay.
So like the index contains the embedding.
Yeah. Okay. So you have to index the embedding as well. Okay. So one thing that you notice, like most part of this lab will be covered in the next lab in the next lecture. Okay. So meanwhile, you can go through, read all the instructions. Okay. If you have questions, just write them down. And in the next lab, we will reply all the questions. Huh?
We'll have to respond.
Yeah, this is a long lab. That's why you're given much more time to go through it.
How do you respond to that?
I don't check the deadline model. I don't. But one thing that is good here is that you have things that are already done for you. For example, you have the function to split half. So to index, we want to not have everything in the same file, okay? But we can split them and store them in different files. Where we just have the indexes, okay? So after running this, you should have the chart in different branch of files with the capacity that you define, okay? 20,000. And then you have the get data set. So since you know where you store and you index your files, Okay, you can then do what? Loop through all the files and then load the files, load the content and return them. Okay. And then you have the iterate dataset. So basically you should return what? An iterator that should go through all the elements sequentially, opening the files. So this is the first function that you should fill up. Okay. And next we start the task itself. So first you have to build a geospatial indexing. Okay, you can build it based on BAL tree or KD tree. So these trees are the data structure that can make it easier, for example, to find the K closest point given a particular point, okay? Or find the points that are located in the specified regions. All the links are there for you to explore. So since you have the data structure, applying KNN is pretty straightforward. You just have to query your data structure. So if you check this documentation, you will see that there are queries there where you can query by finding the K closest, or you can query in a specific radius. This is what in radius we do. So if you are given a list of points and a radius, you want to return all the data that are located around the radius of that point. Okay? The same with KNN. I'm given a point, I want the K closest one. So remember the BAL tree, very straightforward to implement it. Just with one line of code, you're done. Okay. And then you can build the geospatial index based on what you have here, which will return what? A BAL tree that you can query easily. The next thing is that you have the asset to make sure that it passes all the assets if you are given a point and a KNN. So these are the assets to make sure that, okay, your query, if you find all the points that are located around a particular point, that point is part of the result, okay? Even if you find the K closest point, it should also be part of the result. So you should make sure that your code passes all those assets. Also, in this optional case, you have the chance to check how the size of leaves influence the search. So this leaf is how you define the BAL tree data structure. Again, we covered this in the next lab, in the next lecture, details. This is the bonus task. And what about the range of query? So if you are defined, you have the northeast and the northwest coordinates, okay? So can you return all the points that are located around that region? Remember, we indexed based on the coordinates. Okay, since we index based on the coordinate, we can easily find the points that are located in that range. Okay, so that's what the function getInRange should do when you're given those coordinates. And then there's a function to print it for you that will be used to print your results. And one thing that we can do is that if we give these coordinates as northwest, northeast, and then we give the coordinate of southwest, okay, we are expecting to see Manhattan located in between this coordinate. Does that make sense? So these are the things that your code should pass, and then you have all those points that are located in between the coordinate that you have. Another thing is about the geocoding. So now we want to convert a text. So you give a place, okay, we convert it into coordinate that we store. Okay, so if I'm given, for example, Innopolis University in this query, it should return something. I think I had this somewhere here. So if my query is Innopolis, don't copy my Cape code, please, as I'm recording. University. So if I run this query, so it returned what? Return the street, okay, the road, all these things, and also it returned, you can see in the viewport, in geometry in the viewport, it returned the northwest and the southwest coordinates of Innopolis, like the region. And then I can look for a coffee shop that are
So I
inside
think
that
that
place.
we're gonna have something like this.
Have what? Yeah, you're using the geocoding. You can use Google Map, there's a link here, if you want to get the API key. Okay, so we are querying Google Map to get those data, okay? And then we can index them. That makes sense? So the function will return a pair of northwest and southwest coordinates given the query. I showed you in the JSON where you can get them. And remember, you can use what? Request.get. Okay? In request.get, you read the JSON and return those coordinates. And then we can then get the town's range of, for example, this city, as we did before. So we expect that it should be located, this point, this coordinate should be in between. Okay? The coordinate of this town should be in between. Does that make sense? Right. And then we want to find to query the cities that are located in between a given coordinate with northwest and southeast. So here we are given the index that we have. We also have the maps key, have the towns. Okay, so this will return the data set of indices. Remember, the indices are in geocode. Okay, so if we are given, for instance, Wheatbush downtown, we want to get all the towns. So we want to find all the points inside. Remember this bunch of points. Remember this bunch of points. So I'm giving northwest and southwest. I want to get all the points that are in between. Okay? Well. And another thing is that we want to implement caching. One thing that you should know is that this library is not free. Okay? So every time you query, you can get charged. Okay? There's a cost for each query. Okay? So why do you want to spend money if you want to run the same query? So it's something important to catch the query. Okay? So here you have the global geo caches. So when you query a town, if it is already existing, you return it. If it's not, you query, you get the coordinate and you store. Okay? So that's why you should actually expect to do in the cache.
So like this thing is free, right?
Well, yeah, it's free for the initial use. Okay, they have free trials.
How many requests?
A lot, enough to completing the lab. Okay. And then you have, and then you can test this. All these things just for the test. So if you are given get towns that are located here, okay. So you do all the job, it goes, return the northwest and southwest coordinates, and then find everything that's in between, okay? And you can see it returns all the towns. And then you have the text search. In the same manner, we can embed it. So if you want to run the query, for example, let me go straight to the example. So you have to embed the text first, okay? To have the embedding of the text that the query that you're looking for, okay? So here it is, we are using Scarpy. You can use anything that we did before. So you have 5.3 from this lab, okay? So you can use anything that we did either in this lab, or you can implement the Spatie. You can use the Spatie implementation. So basically it returns you the embeddings, okay? And based on the embeddings, we will run the queries, okay? So what do you have? You have vector index. So if you have the embedding of the vectors, okay? You can still query by checking, once I have the embeddings, with my data structure that will have a ball tree, I can also get the KNN clauses. So I'm indexing using the embedding of the queries. Okay. So, and then you have to put everything together where you can find towns given a query, and then you expect to return data item with coordinate and text. Okay, so here we do not expect you to have exactly the most accurate result. You can improve whether you want, but you should return something that your embedding gave you. Okay, so the indexing should be based on the embedding that you did, and then you return the result from the data set. So if we are looking for, in Manhattan, we are looking for hospitals. So this should return not exactly hospital, but something that is related to hospital based on the embedding. Okay? Right. So that's pretty much it for the lab. We come back to this during the next lab. So for you, I'd really advise you to go through all of
What
it.
is master, bro?
It's your task. This is advanced level.
Use. What is this like extra one?
What?
Is that in? Yeah.
Yeah, so there's an exact task here. So go ahead and go through it, start working. If you have questions, we discuss it in the next lab, or you send me a message on Telegram. Okay?
So that's why it has 20 days.
Yes.
Next one video.
I don't think we have a lot more time. So online, please send me your email addresses. And you please scan the QR code. I'll stop sharing. Sorry.